Hello everyone and welcome to this new lesson of the Archival Line Academy, the public training program of the Digital Center Archive of the Fondazione Giorgiocini in Venice. Today's lecture is entitled AI and Heritage, Practical Skills for Extracting Information from Historical Documents, and is the first in a series of 3 sessions led by the team of the Digital Humanities Lab at EPFL. So today we are pleased to welcome Frédéric Kaplan, Director of the DH Lab, along with Paul Gerneck. I would like to remind participants who require a certificate of attendance to follow the instructions provided in the chat. So now I leave the floor to Frédéric and Paul, who will explain the specific objects of the workshop. Thank you for your attention and enjoy the lesson.
Thanks a lot. Thank you very much. Welcome to each of you. We're very pleased to see, that there is such a good attendance for this series of free lessons. The subject of AI and heritage is a growing subject. There are more and more elements that could be said about it. It's going to play an important role and a growing important role in the coming years. AI is likely to be used in many processes to extract information from historical document, to link document with one another, to transform a document of one time in another time. And so little by little, it is likely to play an increasing role in various aspects of research, of course, but also of curation and other forms of activities which are linked with cultural heritage. The idea of these 3 lessons is to be concrete, to start with a concrete example, and to go also at a pace that will enable you really to learn concrete skills. And so this is why the program, which has been prepared by Paul Gerneck, is really walking you through a series of steps, starting on a very concrete case study that he will explain in a minute. If you actually find these elements interesting, which we hope to, don't hesitate also to contact us. To learn more about potentially the other aspect. Of this intersection between AI and heritage. The more you will be in understanding the importance of the skills. The more effective will be on the entire sector, which is essentially what we are aiming for. One point before we're starting, we've been conducting workshops like that in different settings. It's so helpful if we can switch your camera on for us. I know sometimes it's not so practical. Maybe in situation where it's actually more comfortable on your side to have your camera off. But I can guarantee you that when we're teaching, it's actually much better to see your faces and understanding if you have questions. Don't hesitate to raise your hand if you have an element of oops. Okay. Was I muted?
Just the last 2 seconds.
Yeah.
Did you hear the beginning? You heard the beginning? Okay, yeah. So yeah, don't hesitate to stop Paul at any moment on the process. The idea is again to not having only a frontal lecture, but actually having you the possibility of experimenting and learning at your own pace. And of course, we'll take also your feedback after this first lesson to see whether the pace was right and how we can potentially adapt in the 2 forthcoming lessons. Unless there are any pressing questions, okay, I give the floor to Paul for this first lesson.
Okay, good afternoon, everyone. It's a pleasure of seeing so many of you. As I think was mentioned by Frédéric, and also as was detailed on the website, the structure of the 3 lessons is going to be relatively stable with some possible adjustments if need be. But all 3 lectures will be 2 hours long, with 1 hour of theory / contextualization, with many examples that will be given in a lecture format. By all means, do interrupt me if you've got any questions. And the second half of each session will be a practical hands-on tutorial in Python, which I have prepared to go along with the lectures and to make it extremely concrete for you to understand what we mean when we talk of using AI in heritage research, curation, etc. I am aware of some differences in the levels of familiarity with Python. So every example and notebook has been thought of to be quite easy to follow. And there are some more difficult questions for those of you who want to be a bit more advanced. But the idea is very much to get a hands-on and a feel for what is possible, what is not possible, etc. Okay, so let me start with this lecture. And again, I insist, do stop me if you've got questions at any time. All right. So what do we mean exactly when we talk of using AI in an heritage setting? The title of the lecture series is called Practical Skills for Extracting Information from Historical Documents. And everything is already hidden in that title. There's going to be a mix of practical skills applied to some historical documents. And the goal of that is really to extract information for researchers. Those researchers can be yourself. In my lab, led by Frédéric, we have this history of extracting the information ourselves and then using it as well. But it can be other forms of institutional settings where you extract information for other research projects, etc. So just to show you concretely what sort of things we can do when we intersect AI with heritage and archives, I'm going to take a series of examples from the long history of projects that our lab has been running for the past 10 years or so, from different scenarios, different sort of documents, etc. The first subset of those concerns urban analysis, more broadly the history of the city. It's something that I have recently concluded my thesis in, and something that has long been a study of both the lab and the archive center where this research is taking place. As a first example, I'm showing you here the 1808 Napoleonic Cadastre of Venice. It's a document that was compiled in the early 19th century when Napoleon enforced a new administration of the city, and for reasons of taxation, he had a map drawn of the city. It consists of about 20 sheets that each represent a different section of the city. And so when we realign them on a physical space, we make sure that they align, etc., we get a full map of the place, and we already reconstruct this early 19th century state. But of course, what we want to do, if we are interested in urban analysis and urban history, is to look perhaps at the average rent or the number of owners or the large ownership structures, etc., information that is contained in that document. Of course, because this is such a large document with thousands and thousands of entries, doing this manually is not possible. And for a long time, it was mostly done on a case-by-case basis. What we could do using the techniques that we're going to be discussing in the upcoming sessions is going from this paper document to its equivalent computational representation. And the two are, let's say, the second is a transcription of the first, where we have restored the geometries of the document, but we have also attached information on the owners, the rent, etc., etc. Because it's a computational document now, we can do the sort of analysis I've mentioned. So we can look at average rents, ownerships, etc. We can take another example. This time you are looking at another document, not found in the State Archives of Venice, but in the National Library of France. It's a map of Paris drawn in the late 18th century. It's called the Plan Wernicke, and one could be interested in the urban structure of Paris at this time. What would be tempting to do is, of course, converting this rich plan into a street network, for example. Myself and some colleagues, we have long studied the evolution of street networks, and what we could do is converting this into a set of streets. Redrawing them manually is very long, very hard, and that's why it's quite rarely done. Turns out we can leverage AI to do part of the work for us, and going from this document to this computer representation. One of the promises of AI, of course, is that it is general. That's the sort of meaning behind intelligence in the title, that it can adapt to different scenarios, different documents. So following the same logic of extracting street networks, we can basically repeat this for many, many maps. And in this case, just to illustrate what I mean, we have been working on about 500 maps from the French National Library, repositioned them in space, and for each of them extracted the street network like I've just shown you. And when we superimpose those, then we start to get interesting information on the proper evolution of the street network. And new kinds of calculations open up. What is the effect of opening a new street? How has the city evolved along with the explosion of its population, etc., etc. Another example, and always in this theme of urban evolution, is doing the same thing, but not with streets, with buildings this time. And this comes from another project of the lab, led by Beatrice Vaianti, who's a PhD student studying the cartographic evolution of Jerusalem between the 19th and 20th century. And again, using the same logic of gathering information from local archives, in this case, archives in Jerusalem, we have been able to extract the presence of buildings across 100 years and convert that into a video showing the evolution of the urban shape of Jerusalem. Now, this is showing you in about 30 seconds, 150 years of building creation as the city gains importance in the region. I should insist that all of that is done manually with, of course, some steps of manual verification, but it's the sheer usefulness of AI that allows us to automatically model thousands and thousands of buildings across hundreds of documents. The reasons I draw these use cases together is that they all follow the same logic, the logic that we will employ to use in these coming lessons. Right, so for now, I've been looking at examples from the cartographic side of documents, but cadasters and other administrative sources also have other kinds of information, namely textual information. In this case, I'm showing you another example coming from another archive, but which shares the same problem, the Archives of Lausanne, where we are based. On the left, you see a map of the kind you've seen before in the case of the Venetian Cadastre. And on the right, you see a zoomed in section of the other part of the document, which describes for each house the surface, the price, and the usage of such information. But again, we can somehow train an AI to recognize this information, transcribe it, and store that into a data structure that we can then query, leverage, and play with. So I'm showing you here concretely what I mean. We can click on a building, on a parcel, and automatically we have managed to transcribe the ownership and the use of each of those parcels. Incidentally, this is the subject of an upcoming book from our team. And then from now on, we can do urban analysis. So I mentioned in the introduction that we can study domain owners in different states of the city. So here I'm showing you the first 10 families. We can study the kind of property it is. We can study the type of ownership itself, etc., etc. Okay, so and then as a final case study in those examples of urban history, I'm showing you Venice. A previous paper by the lab has shown how inside this cadastral information, we can extract automatically some form of structure relating to the economic landscape of the city. In this case, you see notably some sort of heterogeneity between the regions that accumulate commercial activity and those which accumulate typically warehouses and gardens, etc., etc. Okay, on to another area, another branch of case studies, not so much dealing with urban history, but perhaps more with art history, and closer still to the Fondazione Cini's preoccupations. Over the past 5 to 10 years, my lab has been working on digitizing the hundreds of thousands of cardboards contained in the Cini's Fototeca. Many of you are probably familiar with it. It's a unique and fantastic resource for anyone interested in art history, both Italian, European, and world art. This long project has needed many different components, both software and hardware. I'm showing you here the two very impressive scanners that have been done precisely to digitize this massive archive efficiently. There are rotating scanners and the pictures are taken from above. You can see an example of some of those cardboards on the right. The sort of documents that we get, on the left, you see the long corridor of the Fototeca and the hundreds of drawers containing each hundreds of postcards, photo cards. The sort of documents we get is seen on the right half of my slide, and you see they all seem to have a relatively stable structure. They've got a photograph of an artwork in the center. They've got some text information that is either handwritten but mostly typed in the top, typically place where the artwork is based, a short description, eventually a title and an author, collection numbers, etc., etc. So what we have done, using the techniques that will be the subject of this series of workshops, is train AIs to separate this initial scan, which you see on the left, and separate that between the visual components, the artwork, which you see on the bottom right, and some form of metadata, which you see on the top right, separating between the author, the description, the city, institutions, etc. What we end up here is effectively a database of images which have metadata. And this can be the starting point of so many queries, so many research dimensions. The first one is perhaps a low-hanging fruit, but nonetheless very interesting, is studying how the different collections or sub-collections within the Cini's Fototeca are interested in different areas and time periods. I'm taking here two very representative cases, the Alinari, which mostly focuses on the Quattrocento, early 16th century, and the Museo Correr in Venice, which has a strong bias in the 18th century. We can also study the temporal distribution of all of the artworks. And again, this is something that is perhaps unthinkable without the use of such techniques. The reason I'm saying this is that simply manually typing in 300,000 cardboards is a very, very heavy, if not unthinkable, task. So being able to bring in AI tools into this is a strong asset. We can also move a bit away from what is contained in the document itself, and this is where other forms of techniques come into play. For example, here we can look at the geography of the corpus if we align the artist names we have found on our documents with some kind of database, like typically Wikidata, which would tell us where such artist was at such periods. And by repeating this for the hundreds of thousands of documents, we can recreate the artistic nodes that are contained and represented by the Cini corpus. Side note, this is exactly what we're going to be doing, aligning this cardboard onto other databases. This is the subject of the third and final workshop. We can also look at the other parts of the archive, the photo itself of the artwork, and leverage some other forms of computational techniques, typically to detect identical works across the phototeca. This is something that is quite powerful and really full of surprises, because it is simply, almost mathematically impossible to compare all possible images, especially like in the case of Cini's phototeca, where the same painting might be found in 4 different sections of the archive, filed under the author's name, filed under the museum that stores it, or filed under the place it's at or was in the past. So this has brought us to many interesting surprises, showing that, for example, the same artwork has been described as being painted by 2 very different painters, thus being the starting point of an inquiry into who exactly is the painter of this Gabriele. Okay, right. Perhaps I should stop here for a second as we move on to perhaps a more practical aspect, and ask if there are any questions that you would like to raise. Okay, doesn't look like it. So I'm going to move on to a closer look at what happens under the hood in the computation. So I try to design this series of lectures and courses with a generic structure in mind, something that each of you working with different archives might be interested in. The core idea that has been leveraged in every single case that you have seen so far, no matter if they talked about maps, cadasters, images, text, etc., is that of supervised learning. It is a form of machine learning, or AI, that works as this little drawing is showing you. It starts from manual annotation. So you, as a researcher, would tell this software what exactly you want to do. So in this case, I'm showing you a small extract from a map in Lausanne. And let's say you want to identify what is a building and what is a field. So what you would do is annotate tens, if or hundreds of images, it depends on what you want to do, showing, okay, this is the original image, and this is what I want you to try to do. In this case, I want you to draw the buildings as pink and the fields as green. This phase is what we call training. And the dream of that is that once the AI has been trained, it's able to infer. That means to be able to apply this capability, this ability, to new data that hasn't been seen. And therefore, we don't need to manually do it anymore. The AI will do it for us. Of course, the interest that we have in doing this is that we only need to train for a small percentage of the corpus, typically 5%, thus freeing 95% of the time it would have taken otherwise. And of course, you can imagine that if you have very large archives, like the Cini's, for example, the time gained is simply unmatchable. So concretely, if I'm taking again the first example I opened up with, what we would do in this case is simply choose a section of our corpus between 5 to 10% and manually annotate it like that. So this is only one of the sheets. And then if the training has been done properly, we can then extend it to the rest like that. This idea of training on a small sample and then expanding this to the rest of the corpus is the basis of any form of AI usage, of supervised AI usage in archive research in historic collections. Okay, I hope this is relatively clear. Now let me get to what exactly we're going to be doing. And what we're going to be doing is to follow all of the steps that we have put in place in the case of the Cini Fototeca. I've created two figures here to help you understand, and I've placed the different sessions of our course on here. So the first one would be to go from the scans, which you see on the left, which are available and they are foundable online, to a first segmentation. This is the step you sort of see in the center that splits the image between the text component and the image component. So session 1 is what we're going to be doing today. Session 2 is focused on how we go from this text segmentation to a structured database. Namely, how we go from a series of characters to a proper structured database that has a column that says the author is this, the description is that, the city is that, etc. And the third session, or the third topic of our course, is what exactly can we do to enrich this database? I've mentioned connecting it to other forms of databases, mainly open access, but also what sort of calculations can we do, for statistics that you might be interested in, etc., etc. This is what we're going to be doing in the last session. And then the fourth bit, which we won't have time to cover, really concerns visual analysis. And this is something that is perhaps more advanced and therefore would require a dedicated course. Okay, so moving on to today's content, which is this first section of my big diagram, how we go from the original scan to regions of interest on the image. Well, let's see our plan of action of our general structure of AI learning again. In this case, what we are training the AI on is a set of labeled images where the cardboard has regions identified. And the regions we want to identify in this case are what is the image. What we want to do is extract the artwork picture, which you see pasted in the center, away from its background, away from its cardboard. And in the hopes of course, applying this to all of the other cases that we haven't seen so far. So, principles of learning, again, we've got the input image, which is your typical Cini cardboard. We've got a ground truth, and I'm going to come back to this in a second, which is the manually annotated truth of what we want to do. And the goal of the AI is to learn how to make the two match, how to predict what's going to happen as precisely as possible. This is why we need the annotation. At first, the AI is going to try almost at random to predict where exactly is the image, and by comparing it to the ground truth, and by then adjusting itself to better its results, it's going to progressively get better and better, and hopefully be a perfect fit for the task. This moment of comparing a first attempt with the ground truth is called the comparison. It creates an error, which we use then to adjust the AI. You repeat the circle again and again and again, and the more you repeat it, the better the AI is at learning exactly the task. Oops, sorry. So this is the general structure that you will see in every form of training. In this case, moving from the cardboard to the annotated labeled image and the extracted picture is done in two phases, the training and the inference. For technical reasons, we won't have time to do the training itself because it's very computationally demanding, and also in this setting of 70 people, so it's a bit too difficult to walk through it. It takes time, etc. So what I've done is sort of training the AI we're going to be using so that it's already done for you. You don't have to train it. We're only going to focus on the second part, which is the inference. Now, a small note on what it is exactly I mean by annotation, and this is more for you to know and potentially apply in future cases than for us this week. But what I mean by annotating is giving it the truth, the result you hope to obtain. In this case, again, what we want to obtain is a sort of copy of our original image in which we have identified the artwork we want to get. This is the task, identifying the picture of the artwork in the center so that we can then take it out and export it in a different file. To do this, we need about hundreds of examples that we do ourselves manually. Typically, you basically copy the image in Photoshop or GIMP, and then you create a mask that you feed back into the algorithm. Something that is quite important and is perhaps more conceptual for you to know is that the AI has nothing more than the image to use. So what you need to do in this annotation phase is to remain as close as possible to the image. Never annotate anything that is not contained in the image, otherwise the network will never be able to learn from this annotation. Any form of information that you hope to train the network on has to be visually embedded, has to be contained in the image itself. This is something equally true in maps, text, or images, such as this one. Okay, so the second half of the pipeline, and the thing we're going to be focusing on in the workshop in a bit, is this inference idea. How we go from a train AI plus some images to a label. Okay, so this is so much for the context and the sort of general framework, motivation, etc. Of why we use AI and what it is exactly we're going to be doing. I have a third section on how exactly those workshops are going to be structured, but perhaps this is a bit more removed from the lecture itself. So again, I'm going to seize the opportunity, and if you've got any questions, by all means, this is the moment.
Yes. Hello, I have a question for Mr. Guenet regarding the apprenticeship of the AI. So you talked about the fact that the AA was reproducing what it has been told to, but what about the possible errors that the AA can do, and also the part of misinterpretation of the AA during the transcription or the learning of all these things? And also you talked about extracting the image, but what if the ground floor, yes, the ground of the paper is also an image? Because if there is an image, so if the paper is still an image and you have, for instance, another image glued on the top, so it makes two images. So what if the ground floor, what happens if the ground floor is also an image?
Yeah, okay. Well, thank you very much for those two relevant questions. The first one, perhaps something that really should be emphasized, is that yes, this algorithmic training and the use of AI is a remarkable shortcut, but of course, as you've mentioned, what it produces can have errors. So anything that you want to use as the starting point for historical inquiry has to be manually verified. And indeed, in all of the cases I've shown you, there has been steps to correct the small mistake here and there, to adjust geometries on the map, to detect or to make sure that there is no spelling mistakes, that sort of thing. It is absolutely paramount, yes, to keep in mind that while AI shortens the time for repetitive tasks, it comes at the cost of having to verify it. But hopefully the trade-off is good enough that you still end up gaining some time. And on the second part of the question, it comes back to what I was saying at the end of the lecture, which is the importance in training for visual consistency. So if you are in a scenario where there is an image on top of another image, how would you should ask yourself, how would you differentiate the two yourself? Is it because there's a border? Is it because one image is much dimmer than the other, or fainter, or I don't know, pink, whatever, etc. And then you should also know that AIs are only able to detect those if there is enough repetition, if you have enough examples that it can learn from. Otherwise, the visual consistency is not enough to train anything, but it's also not enough to justify using AI. So again, if there is enough repetitions, then the AI might be able to detect it, and you might be able to properly train the model. But thank you for the questions.
Thank you.
Sorry. A question, please. Which kind of AI do you use? A proprietary AI or a commercial AI?
Well, as research institutions, we tend to always use open source models, either things that have been developed by other universities or things we have developed ourselves. And in fact, the thing that we'll be using today has been developed by the lab, is completely open source, so anyone can use it for free, of course, tune it, modify it, etc. Yes.
Thank you.
Any other question? Okay. So moving on to the last and even more practical hands-on section of my presentation, which really tells you how we're going to be doing those workshops. And this is what I've been calling the coding environment. I've mentioned in the introduction that everything that we'll be doing will be in Python, which is a very popular and nowadays common programming language. It's very versatile. It has an incredible ability in many different scenarios, partially thanks to libraries, which I've given a few examples around. So there's PyTorch, NumPy, Pandas, etc. Those are, you can think of them as sort of collections of tools that are made available for Python users for free, and which you can combine, leverage to do different things. So typically PyTorch is the thing we use to train neural networks. NumPy is things that are very good with number calculations, and Pandas is good for data sets and table structuring, etc. So we'll be using Python. Now, because this is an online course, I know it's quite difficult to make sure that you all have Python installed on your computers, also because some of you are not very proficient yet. So what I've done is setting up an online working environment through Google Colab, which is a free app that is made by Google to allow people to interact and run some Python code. I've put every teaching material at this address. So what I suggest we do before I move on to the next session is that you all go to this address, those of you who want to do the Python tutorial, and you start downloading the material that is there. And what you're going to be finding is a set of images, code, etc., that you can download, and then we will put this on your Google Drive. I'm assuming you have a Google account because it seems to be a mandatory thing of 2025. So if you do not have a Google account and that you wish to proceed with the tutorial, I would suggest you creating one, perhaps just for just this workshop, etc. Okay, so I hope the address is visible.
I put it on the chat also.
Okay, thank you. It's about 150 megabytes, so I hope your connections are stable enough. Yes, and then what you should do, so this looks like this, and you'll see a set of inputs. There's going to be 3 folders: input, output, and training. And the last thing is a Jupyter notebook, which is a form of interactive way of running Python. I'll go back to this in a second. So it should look like this. You should download it like I've done and place it in your Google Drive account. Any questions on that? Okay. It shouldn't raise a problem, but sometimes Google blocks the download of too many people if everyone's trying to download the same thing at the same time. So if this is happening, do let me know and I think of an alternative solution. Okay, so while this is downloading, I'm just going to give you a brief introduction to the sort of environment and things we're going to be playing with very concretely, for those of you who don't know, perhaps. So Python is a programming language, meaning that it's got a series of text commands that you can combine to do a variety of tasks. And one of the ways you can interact with Python is this thing called notebooks, which you can sort of think of as an interactive Word document, if you wish, where you can run code. Especially the many flavors of notebooks, but one of those is the one we're going to be working on, this Google Colab version online interface. It looks like this. It's very much a screenshot of the file we're going to be working on today. And this is what the interface is like. So for those of you not super at ease with it yet, let me just decipher what you see. So in red here, you see the code cells. And this is where the Python code is actually stored and from where you run it. The things you see, the lines you see starting with a hash, are comments, and I've written them so that you understand what the lines of codes do. They do not matter in the running, it's just for you to understand what it is that we're doing. Below each of those cells, you will find some outputs, and it tells you what the cell above has been doing. Sometimes it returns some text telling you, okay, I've done the instruction, it worked. Sometimes it returns you an image. Sometimes it returns you nothing. But this is the place for you to check if the code is working properly. So it's always a code cell, a code output in alternation. Importantly, code cells, and this is one of the specialties of notebooks for those of you who know Python perhaps in the more usual standard way, they are thought as independent cells. So you can run one without running the other, which is not your typical programming way, let's say. And to run such a cell, this is quite important, you use the shortcut Shift-Enter. And the reason I say this is because it's quite hard to find on the interface of Google itself. So try to remember Shift-Enter as a way to run the cell and move on to the next cell. But of course, I'll remind you this if the problems arise. In the notebook itself, there are other bits and pieces. There are text cells, which you can see have a different font, etc. This is where I've put longer comments and instructions for you to do with questions.
Apri il tuo e trascini come se spostassi un'icona dentro.
Sorry, was that a question? Okay, I'm assuming not. So text, comments, and instructions is what you see in between the cells. On the left, you'll see at some point a file explorer. This is where you're going to be making sure that the files you want to create or upload are properly located. But don't worry, we'll go through this in a second. To access this, sometimes you will be asked to give access to your Google Drive folder. So don't be alarmed when you see this. You may want to consider having an independent account if you want to completely dissociate your usual Google Drive from this project. And then finally, and this is a technical detail which I will emphasize again later, on the top right, you see an option to choose what's called a runtime. So think of it as a way that the notebook is being run and what sort of computer power it uses. This is important because we're using AI, and AI needs larger resources than usual. Typically needs GPUs, for those of you who know that, and which is why it's very important for you, in this case, in our workshop, to select it and make sure that you have GPU selected as your runtime. Otherwise, the thing will not work. There's not enough processing power, and it may cause some issues. Okay. Right. So I think this is all that I had to tell you for the environment itself. I hope that by now everyone has downloaded the thing in the background, perhaps even uploaded it on Google Drive. And we are ready to move on to the second half of the lecture.
Maybe if there are some, I guess maybe some of you are experiencing troubles or issues, maybe don't hesitate to ask now. If not, you'll actually have difficulty to follow. And I'm sure don't be afraid to ask, because if someone has a problem, many other people have the same problems usually.
I see in the chat an important question. Do we need to have Python installed as well? Not at this stage, because precisely to avoid compatibility issues, etc. Everything will be done online, and the Google Colab interface has Python installed, sorted, etc. So you don't need to have it installed. Someone asking if we need to use the GPU. Yes, you do. Yes. How can we change the GPU? So let me bring the slides back up. So what you see at the top right here, this is your standard interface app. I'm guessing that you guys are all in Colab. If not, yes, maybe I should have said this first. This is once you're in Colab, and once you are in Colab, you can click on the top right, and then change the running time to GPU in change running type here.
There's a question, how do we go into Google Colab?
Yes, okay, so this is, so what you guys should do is, assuming you're connected on your Google account, I'm going to share my screen. Yes. So assuming you are connected on your Google account, you can go to collab.research.google.com or just type Colab Google into Google, which will take you to this page. It will most likely ask you for which notebook you want to open. And in this case, if you have uploaded the notebook and the other folders onto your Google Drive, you can click here and you are taken in this interface. Okay.
There's other person that could not open the file. Maybe if you can show again the first steps, Paul, where we click on the URL, initial URL, and show with the URL which is now in the chat typically. Just making sure.
So the URL is this one, and you have, if you are connected to your.
But I mean, I think the URL of the resources itself. I think I would.
Oh, okay, okay. Good.
Wow.
Do you want me to share the resource again?
Maybe. I mean, I guess this is maybe one issue. I mean, for the person which is not capable of opening.
Okay. So if we go there.
Exactly. Okay, so here you have the three folders. You have
Yes.
the files of the actual logbook, and then what is exactly the next step people need to do?
Right. So they need to download everything here. Genie demo. This might take a bit of time, and then upload that onto their Google Drive. And if this has been done properly, then when logging onto the collab, this file will be available and clickable.
For those who have the issue, I mean, don't hesitate to speak up and ask, making sure this is solving your problem or not.
What we can also do is I can simply walk through the notebook. For those of you who haven't managed to open it up, we can walk through it together with the screen sharing. And if you want to interact with it, you can send me an email, and then I make sure that you have access to it during the week on your own time if you want to interact with it. Okay, so this is working for Erin, seems. Any by raise of hands or chat, is it working for most of you?
Okay, let's move on.
Okay. Okay. So if you have this visible, then the first step is to connect to a runtime, like I've explained at the end of the lecture. You can click change runtime, make sure it's the GPU, you save, and you connect. Sometimes Google Colab will ask you if you are indeed a human. Click yes. Okay, so I am now connected. My notebook is open. It's working. I have managed to connect to a GPU. Everything is going well. I hope most of you are able to do the same thing. And if you are, you can start reading through the text. There's a small introduction telling you what it is exactly we're going to be doing. It basically reminds you of what I've been telling in the introduction, which is that the 3 workshops will decipher or dissect 3 different parts of a typical AI and archive pipeline. And the first of those steps is how we move from an image scan to its regions, its segmented version. Okay, so going slowly but surely, the first part of the notebook is to prepare and set up the different libraries we're going to be using, the different resources that we're going to leverage. So the first one is we need to connect our Jupyter Notebook with our Google Drive account. And this is important. That way we can upload and download files like I've been asking you to do a bit earlier, and we can access which images we want to analyze and get in the end the images that we have processed. So to do this, we import the drive library. This is the first line, and we mount it, which is the term to say we plug it to the notebook. So to run the cell, either you click on the little play icon here, or you do, yes. It will ask you if you want to give it access to your Google Drive. You say yes. Continue, and it should be fine. You see it takes a bit of time to load. And then it outputs that it is mounted. So if we open our File Explorer on the right, we're very happy to see that our drive is here, and we will find the data we have been uploading. Okay, then at this stage, we have properly set the runtime, we have plugged in our drive account, and now we're going to be moving to a long cell. It's going to take about 3 minutes, where we download the core library that we're going to be using, which is called the segment. As was asked by the person earlier, it is completely open source. So you can, for those of you who like, you can modify it, play with it a bit. But otherwise, you just click play, and it's going to install every library it needs, every dependency, etc. So you're going to see a lot of things. Don't worry about them. It'll take a while because it needs to install everything that isn't already prepackaged. I will use this slower moment to recall that in the notebook, you will see some questions that start with it. There are comments that start with question written in uppercase. This is for those of you who are more at ease with Python and who perhaps want some little questions or challenges. They're not tremendously hard, but they just are here to make sure you understand exactly what it is we're doing and how the code is structured. But of course, not mandatory. If you can just follow the steps at first, it's already good enough. Okay, so it's still running. As you can see, the wheel here is rotating, meaning that the code is running. Are some of you at the same stage? Okay. Erin is getting a module not found error. Which part is it? Is it the first cell? Oh no, you got it. Okay, great. Taking a few minutes, but that's expected. That's fine. Any other feedback or? Yes. Okay. So it's finished running on my side. I see that Eleonora is having difficulties. Do you want to ask any?
Well, basically, even though I downloaded the folder, it seems like not to be accessible for, I don't know, it doesn't find it in my drive, and I really don't understand why. Let me see if I manage to, but shall I just try to upload just the, hold on, the file that goes .ipynb?
Yes, that's
Oh,
the
I
notebook.
see. Let me try that one, because I tried to upload the whole folder and it gave me an error thing. Sorry, it's my very first time on this thing, you know.
No, that's quite all right. But what sort of error was it?
Let me see. Gosh. Hold on. Let me just try again as you go on, and if I have other troubles, I'll try and catch up. Just a sec.
No worries at all.
Thank you.
It's just that I will need the other bits quite quickly, so
Yeah, go ahead.
try to sort out this problem.
No, okay, it seems to be working now. Thank you.
Okay, excellent. So run the first styles and then we'll catch up soon. Federico asks if it's better to use Google Colab or an IDE like Visual Studio Code. I would suggest it's better to use an IDE for one specific reason. Google Colab is usually used by people who do not have access to GPUs and who need bigger infrastructures that typically you don't have on your laptop. However, and this is something that I have faced preparing this lecture, it might ask you very quickly for some money to do some calculations. So unless you have tremendous computation needs, you are definitely better off using Visual Studio Code. Also, you better understand how these things work. You have it locally. And it also goes better with GitHub if you're using GitHub, that sort of thing. Okay, so now that everything we needed has been installed, we just need to load them. And this is typically faster. So the way we do this is by importing libraries, and we simply type import and the name of the library. And while this is processing, I can answer the last question. If you're using Visual Studio, I suspect you might run into some dependencies problem and perhaps memory issues, and you will need to go back to Colab to run the AI bits anyway. So I suspect it's better for you to wait for it to be uploaded. But you can perhaps follow on my screen. Okay, so we've got the green tick saying that everything has been uploaded and loaded. And the next step is simply to make sure that the GPUs that we've been working so hard to get are properly working. And this is the point of this step. And yes, we're very happy. We've got 15 gigabytes of memory, which is perfect for our hard calculations. And then the final bit of the preparing step is to make sure that our code fetches the images in the right places and outputs them in the right places as well. So this is what we're doing here. It goes to content drive, which is here, my drive, AOA 2025 demo, and then the images are in input. You can see them here. It also goes and get this pre-trained model, which I mentioned in here. And then it will output things there. And of course, because we haven't done the thing yet, the two folders are empty, but it's all ready. So we can run that. Okay. But now moving on to the actual coding thing. Like I've said, we are using a pre-trained model to predict which region of the image corresponds to what we want to extract, the artwork photograph, and which corresponds to the rest of the cardboard. This is really the point of this task, and this was what the model was trained on. The model needs some parameters to be used. Typically, for those of you who perhaps know a bit more about AI and machine learning, we need to specify what is the batch size, how many classes we have been using, what is the structure, etc. but I've filled it all for you, so you don't need to worry about this. We can just make sure that this is entered into the system by clicking play here. Those of you who are more at ease, there is a first small question, if you feel like it. But otherwise, we can move on to the exciting cell of the code, which is this actual processing. Before I click this, I'm just going to make a quick pause. Is there any question? Is that roughly clear?
There's a question, what happens if I don't have 15 gigabytes?
I'm assuming you've got something quite similar, perhaps 14 or 16. The important thing is that it should tell you something that the GPU has some kind of memory, and if it raises an error, this is where you're into trouble. But if it tells you, 14.9 or 15.13, that's completely fine. Yeah, let me know if this isn't the case. Any other question? No? Okay. You're getting an assertion error, so I'm presuming you may not be in the right run type. Make sure you're in the GPU run type. Alessandra asked
There's also cases about access to the folders. Maybe I don't see the input folders. Maybe the folders are not on the right subfolders for some people.
Yes, you don't see the input folder. Did you properly connect your drive here? And if so, you should see it in Drive, then My Drive, and then wherever you put it.
I see the output folder, so maybe it's an upload problem. See if the output folder is there, not the input folder.
Yes, you could also refresh here, and if, as Frederic says, it's the upload that has been a bit slow and has not been completely updated, you can refresh. And keep us posted. Okay, and the would finish on your Google Drive. If you go on the Google Drive, would you see the input images like this? You see that, okay. And you, okay. Well, sometimes Colab is a bit slow with things. I know it's not ideal, but it's little alternatives. So maybe wait a bit and see if it still doesn't appear. Make sure it's also the right path. Okay.
Also, maybe remembering that I think these lessons are recorded. So, I mean, if at some point, I mean, which of course could happen. I mean, as you're quite a large group, it's possible that some of you actually is not figuring something out. I mean, there's possibility of them going it more slowly and step by step, and hopefully you can do that. You can do that before the next lesson. So sure, we'll share the recording. Yeah.
Okay. Yep. Duly noted, Eleanor. I make sure they're available. But again, do ask questions. I think we've got enough time. And those of you who want to be faster can go faster on their own. Okay. Regarding we are now at the prediction process. It is the file. Okay, I see a log hang. That makes sense. So now we're about to predict, and this, what we're doing here is we're going to fetch our model that has been trained and that we have uploaded on Google Drive, and we're going to tell it to do its thing, do the prediction on the images of the Google Drive. So just for you to understand, the images that we want to predict and analyze are on input, and I've really taken a sample of 99 images from the Chini at random, completely random, and they cover everything from paintings, drawings, there might be a bit of sculpture, engravings, architectural plans, furniture, anything you can imagine, to show you that it's a really versatile technique. So this is what they look like. And again, what we want to do is get the image cut away and made available on its own separately. So we've got the model, we've got the images, and by clicking here, we tell it to compute. So this takes a tiny bit of time. I've made sure that we've got a progress bar to show you that it's progressing, and you see that for 100 images, it will take about 10 to 20 seconds to compute. Imagine doing the same thing manually and annotating which bit of the image you want. That is much longer, of course. Okay, so let's load those predictions. We have output them here on our drive. You can see they're here. They've got this NPY format. Those of you who want to answer the question, you can think about what it is exactly that they contain. As a small clue there, they are mathematical objects. They're not images yet, so you couldn't open them in your typical apps. But we can open them in Python because they've been produced by Python. So let's run this. What we're doing in here is simply loading them all, putting them in a list so that we can access them later and play with them. This is the first line. The second line, basically there's the same thing, but for our original images. That way we've got stored at this stage both the original image and the prediction map. Okay, so at this stage we have managed to generate a prediction map for each of our original cardboard images, the ones you see here. Something that should tell us this section is the image. This prediction tells us where the artwork is likely to be found on the image. And as was asked at the end of my presentation, we should absolutely stop to make sure that it makes sense. We should check that the AI doesn't do anything because it's not completely magic. So let's try that. Let's take an image. Let's, for example, take the 23rd. Yep. And we can open it. And this cell should show us the image. This is what it looks like. So it seems to be a part of a crucifixion by Luca Signorelli, which is stored in Cortona. Now, what we want to do is make sure that our predictions do make sense. So we ask, okay, show me the prediction map for this painting. Play. And anything that is not in black is likely to be the artwork itself. This is a heat map. So anything, the lighter it is, the more likely it is the artwork. The darker it is, the less likely it is. So it seems to be making sense. But perhaps we might also want to check the position of the other classes. We are not only extracting the image, we're also extracting what is the background and what is the cardboard. To visualize that, we can define a color scheme. This is what I've been doing here using a Python structure. So we say that the background is going to be black, the cardboard is going to be in red, and the picture itself is going to be in blue. So we can click that. And then by looping over all the classes, we will be able to show what is cardboard, what is picture, what is background. This is what it looks like. And it seems to be quite sensible if we compare with the original image, which is this one. No major surprise, no holes. So that makes sense. Perhaps for clarity's sake, we might want to overlay the two. So basically have the image in the background and then on top of that, a mask to make sure that their geometries are right. So we click that, and this is what it looks like. And at this stage, we're quite happy because our image, which we want to extract automatically, has been detected, no major problem. A bit of noise, this is the black regions you see here and there, because it's not a perfect solution, but we can work with that, no problem. Okay. Any questions so far? Okay.
There's some problem in the find not found for some of the students. I don't know. I guess it's a problem of folder or maybe on the connection with
Yes,
the right. You upload to the right folder.
Probably. At what stage do you get the error? Either Alessandra or Erin?
So again, double check that really what you have on the left looks like that. Drive, my drive, and the demo, and then the free input. This is very important.
Right. Yes, so I'm guessing it's probably because you have put the folder that you have downloaded earlier somewhere that is not the root of your Google Drive account. So if you can see in my case, my drive, I put it here at the very root, but the image you sent, it's Alessandra who sent it. You put it, I'm guessing, somewhere else. So either you can move it on your Google Drive or you can change those paths here. Oh, again, you don't see the input as well. Okay. So it looks like both Erin and Alessandra have the same problem, is that the input didn't download properly. So make sure it's properly downloaded and uploaded. Okay. Anyone else? Any other error? I'm guessing most of you are perhaps following the screen, my screen, as opposed to doing it on your side, which is completely fair. But for those of you who might have tried on their side, does it? Okay. Okay, so if there's no further question, we can move on to the final section of the tutorial, which is the last stage, which allows us to really make sure the whole task is complete. What we wanted, just as a reminder, was to extract the image from the cardboard. So basically create another image that looks just like that. And this is the whole point of training a model, is that we detect where the image is, like here. So now if we want to extract it, what we need to do is to convert this into a sort of mask that we can use to crop the image. The different stages are here. If you want to go through it, by all means, but the idea is to check where the image probability is high. This is the first line. And then get the contour of that using some computer vision. If there are regions that are not the main image because of noise or because of other similar issues, we want to discard them. Of course, we don't want to keep the noise. What we want is the largest blue area in this case. So this is the point of the third line. We only get and keep the largest contour, and we convert that into a rectangle. We can do this because we know the archive. We have looked at many different input documents, and we have understood that in most cases, if not all of them, the documents are rectangular. They're rectangular photographs, and they are placed vertically. Had they been circular pictures or rotated pictures, etc., we might have needed a different strategy. But obviously, our algorithmic tools are tailored to the archives, and in this case, a rectangular selection works well. What we might want to do is also, again, to check, make sure that the rectangle is the right one. So this is the point of those last steps, is to create a rectangle and visualize it on top of our image. So if I press play here, we've got the same image as before, and in green, you've got what the crop would be, the mask of our images. And it makes perfect sense. We're happy with that. So what we do, and this is the next stage, is to crop it properly, to get an excerpt of our image, which we display. And then finally, we can export that to a file that is done like this. So it's now exported. If I go to my output images, we see that the image has been generated. So hopefully, if we go on Google Drive, output, images, up, this is our crop. Okay. So we're happy with this. This is exactly what we've been hoping to do. And now, of course, what we want to do is repeat this step for every image in our archive, every image of our input. So I have left this as a sort of mini challenge for those of you who are familiar with coding. By all means, try to do it. I'll wait a bit, maybe answering questions, and at the end I can correct that. So is there any questions or remark or observations, doubts on what we've done so far?
But also, for some which have the find not found problems, it could be either that a problem about upload, but sometimes it's always a problem where you did not you step maybe you skip a step during the actual in the notebook. I mean, maybe if you click, on step 3 without step 2, this can result, of course, in a file which is lacking. So that may explain in certain cases, I mean, the type of error. So these are the two things you should check. I mean, whether you have your files which are all there, and whether you've been really clicking on each intermediary step in the process.
So I have a question.
Mm-hmm.
Regarding the image extraction, is there a special code in order to extract only a detail of the image or no? For instance, a sword or a horse or a warrior, only a detail. So is it possible to extract by the AA only a detail of the image, or the whole?
Yes, it is. It is theoretically possible. Some projects have done that before. You would need to use slightly different AI things, but it is possible. What you would need to do is this logic. You would need to annotate many, for example, many swords or many horses or many cavaliers, whatever. Train the AI to detect them and then extract that. Of course, the problem that it poses is that there are so many different types of swords that it will take many examples for an AI to understand or to start to understand what a sword is to be able to extract it. So it's a difficult problem. And I suspect that finding a horse is perhaps more feasible than finding a sword.
Okay, thank you.
I see a comment in the chat, someone who's managed to complete the tutorial. Well done. If we change number in the section image number 23, can we try the training with another picture? Absolutely. In fact, the training has been done for all the pictures. This line only refers to which image we take as an example. So for you to see, if we take number 22, just before, and we redo the same steps, you can see it's a different image. Up, the prediction mask has worked. The image has a different predicted region, which works here, etc. And then you can, again, extract the image, basically do all the steps just by changing the image number. So yes, absolutely. In fact, I would suggest you try and play with the different images to make sure that it hasn't been a complete failure.
I'm sorry, I have another question.
Yes, by all
I have
means.
seen that sometimes IA don't recognize the borders of the image. So can it lead to a problem if the IA only take off the greatest part of the image without the borders?
You mean you cannot recognize the borders?
So I think that AA don't recognize the borders of the image. For instance, even if it's squared, sometimes it's a little bit, if I may use this expression, beaten on the edges or a little damaged. So the AA extracts only this kind of blurred borders, but not the square border.
Right. Yeah, so that depends on your input image. If the input image has this unclear edge, like you say, obviously the AI cannot correct that automatically. And then the question depends on what you want to do with it. Do you want to keep the border to be imprecise, precisely perhaps because you're interested in studying how non-straight borders can be? I don't know. Or do you want to correct for that later? Do you want simply to say, I don't care about the shape of the edge, let's say it's straight? That depends on your case study. Both are feasible. In our scenario, actually, this is quite close to what you're describing. The prediction is not exactly straight. You can see here, it's a bit uncertain. You can see it's not quite straight. But because we know the images are rectangular, we are correcting that to straight.
Thank you.
Welcome. Yes, and then to answer Alessandro's question, like Frederick said, you just need to go to the cell, which is at the beginning/middle of part 2, the line that says image number equals, and then you change that to whatever you want to test. Okay. For Loghang, did you make sure that you have the runtime set to GPU and not CPU? I suspect this might be the error. You can send me an email after too, if the error persists. Okay, did any one of you try the exercise? Okay, well, I can correct it myself. So let me go and fetch the code and explain it to you. Basically, to do what some of you were attempting to do in the chat, which is to generate those images for all possible scenarios. What we need to do is find a way to simply repeat the operation we've done for every image. The way we do this in Python is to go through a loop, so-called a for loop, and we say for every image in all of the results, we're going to do the same thing, and that thing is first open the image, then second extract the mask, like we've done here, then convert that mask into a rectangle, and then export that rectangle into an output file. So basically just copying and pasting the different bits from the different cells all together and putting all of that into one loop that takes us through all of the images. So this is the code here. I haven't changed anything, but simply putting things together in a loop. So if I execute this now, you should have a progress bar, and you can see it's quite quick. It only takes 2 seconds to generate that for 100 images. And if you look here on the left, we've got all of our images generated automatically, so we're quite happy. And they start to appear here in our Google Drive. So those are all the cardboards that were in our input. And using our model, we have extracted this hundreds of images quite rapidly. Now, of course, for the sake of this workshop, I've only put 100 images in the training, but you could simply imagine doing the same thing for the 300,000 images we have at the Chini, repeat the same operation, and you will find that this calculation only takes about not even a day to extract 300,000 pictures within the cardboards automatically, which is we have done a few years ago, and it's been a precious resource. Okay, so this was the first step of the pipeline. I think this will conclude the presentation of this first section, how we move from the physical cardboard, its scan version, and then using AI, how we extract the image in the center. We've seen a few steps that involve using a pre-trained model that I have given you, predicting on unseen images like that, and then converting that into crops and then exporting those, which is exactly what we wanted. I hope this made sense. I'm here if you've got any questions.
Obviously, I mean, here you're learning two things. I mean, you see an example of the beginning of the pipeline. Of course, for some of you, it's the first time to use a notebook, the first time you're using Colab. So there's a lot of additional skills that needs to be learned. So of course, these skills will be super useful for any types of tutorial or training you you may encounter if you want to go, I mean, beyond just, I mean, general knowledge, but go in and learn how to play with these things. Because as you saw, I mean, with the presentation of Paul, I mean, that very presentation enables to immediately make experiments, I mean, on your own data and on cases that will be more directly linked with what you hear and the type of context you're in. So it's worth the try. It could be difficult on the first 2 hours to actually jump in, but you'll have let's say 3-4 days to try to redo the exercise, and maybe we can make a kind of check at the beginning of the next session to make sure, I mean, most of the questions have been answered, and you are all up and ready to go and on the additional steps. Any additional questions, remarks? So the video will be available. I mean, I'm not gonna need to check, I mean, but this is with the Gini Foundation system, but we'll make sure this is happening. Don't hesitate to reach out if you have a specific question. And if not, I think we meet on Tuesday. That's right. I think Tuesday, same time.
Do send me any questions or remarks or things you might want me to cover next Tuesday. I think there's a bit of time as well to address those questions, and by all means, any feedback is appreciated. So I think this concludes our first session. I hope it was all right, and yeah, thank you all.
Yeah, thank you both, and yeah, see you on Tuesday.